Okay, if it is clear, now when you combine, right? Where is it come from? For this part. The control volume. This one. Mass crossing the boundary. You combine those. You see there is something in common. The x, y, z. So you take that out because this one is 0. 0 divided by dx dy dz becomes 0. So you will end up having this is the conservation of mass. Yes. Good? Are you good now? Clear? We're just looking for it. Don't worry, we don't even use it anyway later on. Okay? Okay. Guys, this one is only for a Cartesian coordinate. Why we use Cartesian coordinate? Because it is easier for us to understand, right? We love this. When we have a house, usually we have a square. Unless you are a very eccentric person that you do not want to have a cube kind of house, you want to make it round, it's up to you. Then you can derive on a spherical or cylindrical coordinate. But usually we derive it on Cartesian coordinate or cubic side of coordinate. Now, but this one is not necessarily only applicable for Cartesian. You can take a general term, and this one is for any coordinate. You take this become d rho dt, and this one become del dot rho phi. This one is called del operator or nabla operator. Not that nabla, it is nabla operator. Right? And if you hate those, don't forget to put this in your list because this one is more difficult. I will show you why it is difficult later on. Okay, any question before we proceed with the conservation of momentum? Okay. Yeah. This is del operator in Cartesian, cylindrical, and spherical coordinates. Okay. For conservation of mass, if you have a steady flow, okay, if you have a steady flow, which means there is no accumulation, no withdrawal from the container, or when there is no container, whatever coming in has to be coming out. Especially in a pipe flow or in the facet flow where you don't have any storage. Okay, then d rho dt is equal to 0, right? d rho dt equal to 0. Now you end up having d rho u dx, d rho v dy, d rho w dz. And for some even special cases, you have rho is equal to constant. Let's say when you are dealing with water, you cannot compress it. The rho is, usually you take 1000, right? So for that rho constant, you can take the rho out of it. You take the rho out of it, 0 divided by rho equal to 0. So you will end up having du dx, dv dy, dw dz is equal to 0. This one is only for steady state incompressible fluid. That one for steady state any fluid. This one steady state incompressible fluid. Yeah. And lucky for you guys, we will deal with. Most of the time we are dealing with the last one. Okay? Okay? So now this one is some example on how to use that. Okay, if you are given the flow, you can evaluate whether the flow is compressible or incompressible by using the conservation of mass for incompressible fluid. Because you know du dx plus dv dy plus dw dz has to be equal to 0 when you have incompressible fluid. So if you are given those u, v, w, so you will have this, right? This one is the characterization. U dx plus dv dy dw dz equal to 0. This is the requirement if you are having a incompressible flow. So you take u over dx, u dx equal to x, dv dy. You know why it become to x? What happened to y and z? What happened to these two? 0. Why it is 0? Because x. Because x. You sure? Sure. What happens if I have this? Will it give you 0? I change the D from that symbol to D. Will it give you the same? No. That one is partial derivative. Right? That one is ordinary. So you cannot do that. In the partial, if y is not a function of x, it becomes 0. So you treat only the one with x. Okay, in this case, this one is much better. Okay? So you have this, you have that, you have this. This big D is the worst. Because those D anyone got the name D? Okay, those D, the big D is even worse than your naphtha. It's called a total derivative. Okay, I'm not here to tell you about mathematics. So you have du dx equal to 2x and dv dy equal to x plus z. Right? When you combine, you know that the dw dz is supposed to be minus 3x minus z. But remember, this one is dw dz. If you want to get what is the profile of w, you need to integrate it. When you integrate it, remember you have an unknown function of x and y. Because when you take this dw dz, these two will be gone, finished, treated as 0. That's why when you integrate, you need to introduce it back. How do you know this? We do not know unless you do a experimental investigation. You can find out. Okay? But for our class, just put F. That's it. Forget about it. That is your lecture problem, not your problem. Right? But if you do not put this becomes your problem, not your lecture. Yeah? Any question, guys? No? Only conservation of mass, 1 hour. Okay. Before you go, we will have quiz on Thursday. Based on whatever I have in July. Okay, now Newton's second law. Who remember what is Newton's second law? M is equal to MA. Are you sure that one is the correct one? M is equal to MA. Where do you learn it? From 5? From 5, from 4? From 2? Okay. I believe in your fluid mechanics 1, someone has told you that the correct one is what is this? Okay, never met this. Okay, say hello to this Newton's second law. You know why you end up having MA? Because in physics, remember I told you about control mass. In a control mass, the mass is constant. Constant, you have M, D, and your dV dt for a single particle approach that you have in your physics become A. Right? Luckily, in this class, A is not dV dt. We'll have A equal to A equal to lucky, right? Is this good encounter for you? Most of the time you thought that dV dt is equal to A. Now who want to balik kampung? Okay, so boys and girls, now you know what is this D with D that I told you it is the worst, right? dV is equal to the total acceleration, and this total acceleration is the acceleration to the time and to the space. So you have a spatial and this is a temporal or time derivative, and this one is the spatial derivative. You know why it is like that? Because velocity, to be honest with you, it is a function of time and space. Now let me show you some analogy. When I walk to that direction, right? It is only to the x direction. Let's assume this one is x direction. Now I move. In this location, my A is this, right? It's constant. Suddenly I speed up. So you can see my A over there and my A over here is different, even though it is in the same location. Now what happens if still on that direction, but I move, I'm not Harry Potter, but if I can goes up, it will be different also. Now, 2 minutes ago, I told you that I will walk there. Right? Now I walk again, faster, different. Right? So now you know this. U is a very complex thing because it is a function of space and time. Usually we play around with space because you can play with space, but time, right? You just follow it. Unfortunately, it is clear. Okay, so no more dV dt is equal to A. Yeah, it's still A, but your A is now having AX, AY, and Z. And that one, we are still talking about dmV dt only. You haven't touched the Fx, Fy, Fz. And to make it even worse, so you, anyone got books? Okay, this one is okay. When you have a box, there is a force working on this direction. I do that. What I did? Compress it. It's a pressure, I push that. Right? On this direction still. Now, I can do this. Shearing. The shear can be on that direction, can be on that direction. Can you imagine? Only one surface. One surface, I can put the force to that, here, to that. One. Inlet, outlet. Don't worry, it's okay, no problem. Maybe he understands better by doing that. Now you have this only. How about that? Same. 1, 2, 3. This one? 1, 2, 3. Here. Back. Back. You get how many? Okay? That one is talking about surface force. How about the one within it? Your gravity, your weight. Weight is a body force. So you have surface force and body force. Right? In the surface force, you have a normal stresses and shear stresses.